Okay, let's see. There we go. Okay. All right. Okay, that's better. Okay, good. Good morning, everybody. Okay. Let's see here. Just to make sure that my computer is working the way it should, could somebody say something real quick for me so I can check my audio?
Hello.
Okay, working great. Good morning. All right. Okay, so time to get started. Okay, welcome all. Glad to see everybody here. I'm sure people will be rolling in. Let's see, I'm very quickly going to start off by pointing to what I've already sent out as an announcement, but the content syllabus has been updated and I have put on there some an appropriate collection of exercises for those sections that previously did not have any. And so anyway, there they are. And if to whatever extent y'all want to get started, for example, now that we are in fact officially done with section 1.1, it'd be a great idea to go ahead and start working on these exercises now, even though they're not due for a little while, right? It's a good idea to work on those as soon as we finish them in class, because the earlier you understand that, the earlier you do the homeworks, the earlier you will get a thorough understanding of the material, and then the easier it will be to follow along with the classwork that's going to depend, of course, on that. Okay, all righty. So let's see, back to our class schedule. Here we are. There it is. 1.1 is now officially done. We're going to try to get 1.3 and 1.4 done today. I don't think that's going to happen, but we're definitely going to finish 1.3 and hopefully a lot of 1.4. Okay, let's dive in. So here's what we were talking about last time, talking about parametric curves. This is the last one we looked at. And again, sometimes you have to kind of piece it together. In this case, we had this sort of the XY behavior was understood to be a circle, and then the Z behavior was understood to be sort of, upward at a constant pace, and you can kind of put that all together and get that it's a helix. You got to use some geometric intuition there. That's just what it is. Okay, so let's move it along. We're going to consider now a similar question, which is, instead of suppose you have a parameterization, how do you figure out what curve that is? Instead, what if you have a curve and you want to create a parameterization, right? So how do you parameterize curves, in other words? So it's another hook or by crook situation. There is no one size fits all answer to that question. I do, however, have a favorite technique in that this works, I'm going to say, the most often. This is, I don't want to say almost always, that's an overstatement, but this works really often. This is what I like to call the graph parameterization. Specifically, if the curve that you are trying to parameterize is a graph. So that is, and we'll talk about the details more later, but graph means that you have one of the variables solved for in terms of the other. If you have a graph, then just set the input variable to be your parameter. Let's say t. Okay, so it works super well. So for example, here's a graph, right? That's y equals x squared. We know what that is. Well, I'm just going to let x equal to t. And well, if x is equal to t, then unavoidably, this means that y is t squared. Well, that's just, I don't have any say in the matter. And so therefore, position as a function of time, therefore a parameterization. Okay, so real simple little strategy. Again, works surprisingly often. In fact, it works sometimes even if it doesn't look like you're dealing with a graph. So let's take this example here. This does not look like a graph. I do not have this currently written as, y equals. Furthermore, I can't solve for y here, right? You just can't do it. There's, there's a y there and a y there, and it's a transcendental equation. Give it up. However, you can solve for x, right? Very easy to solve for x. And then you just play the same trick. The variable that is the input variable, here I have x as a function of y. So that input variable y, call it t. And then that necessitates x being that. And again, you have yourself a parameterization. What's kind of cool about this example is we just got through parameterizing a curve that we don't even understand, right? I mean, I don't know what this thing looks like exactly. This is a hard. I could probably sit down and really think about it and figure out what this curve looks like, but I've parameterized it independent of that. Okay, let me pause for questions. Everybody okay? All right. Okay, now here's another circumstance. This kind of thing works sometimes. Suppose we have a wheel that's rolling along a road, and let's see, the road is the x-axis, and it's rolling to the right, so it's going, that way. And you can see what I'm talking about here with, the wheel started off right there, and then after it rolled a little bit of a ways, well, now it's over here. And furthermore, this spot right there, as the wheel has rolled, the wheel has rolled somewhat, and that makes this sort of turn around, and now it's way up here. Right? So question, how do I parameterize this path? You might say it's a reflector on a bicycle wheel or something. How would I parameterize that path of that reflector? Okay, so I cannot write this right off the bat as a graph. It is a graph, but I don't know how to solve for y as a function of x, so that doesn't really help me. Okay, the move here is to use vectors Specifically, let's take advantage of the fact that I can talk about that vector between the axle and the point, the point where the reflector is. And that vector is actually fairly easy to understand. Now, keep in mind, vectors don't have location. So when I say that vector, I could just as well draw it there. And that vector, as time goes on, this just represents the reflector rolling around the axle. And it's just doing a real simple thing like that. It's going around in a circle. So that D vector here is actually pretty easy to understand. And then furthermore, this axle, the axle itself is doing something pretty simple as well, right? That's why bicycles ride smoothly, is because the frame of the bicycle is attached to the axle, right? That's going nice straight line. So what we've got then is that the thing that I want to understand, let me use my colors better now. This thing that I want to understand is a sum of something easy to understand, right? And something else that's easy to understand. Everybody see what happened there? So if you're looking at a situation where, the curve that you're interested in is hard to figure, try to think about how it might be points on that curve might be sums of vectors that are easier. And how that's going to present will be different every time. Okay. All righty. So now let's take these two pieces one at a time. Let's talk first about the axle. Where is the axle? This is the easy part. You can see the y coordinate of the axle is always this same value, whatever the radius of that wheel is. So the axle's height is always a. This first coordinate, the x coordinate, that's the amount of road that has seen rubber. And neat fact about bicycles that have rubber tires that don't slip on the road, the amount of road that has seen rubber is equal to the amount of rubber that has seen road. That's what it means to not slip. So it's a nice observation to make. And the amount of rubber, this is actually fairly easy to understand. I mean, because I can just call, I'm going to parameterize by calling this angle here. I'm going to call that T. And, how much rubber are we talking about there in blue? Well, it's just the radius times the parameter T. Let me circle with the colors in mind again. So the x coordinate is the same as the rubber, which is AT. Everybody with me? Okay. All right. Now things are going to get a little weirder where we try to understand that D vector, that thing that's kind of rotating around. And again, keep in mind, it doesn't really matter where we draw it. I'm going to draw it here with its tail at the origin. It's easier to kind of, see what's going on there. That vector, now keep in mind, it's going around that way. And yet that vector is easier to understand in terms of this angle, theta, which unavoidably by definition, I have to think of theta as coming around from the positive part of the x-axis. And if you haven't seen polar coordinates before, we'll talk about polar coordinates later. But anyway, let me just say it's very convenient. I'm going to define theta to be that angle. Okay. So it's very easy to write down that D is a cosine theta, a sine theta, right? That's just straight up trig, really. Okay. But the problem then is I now have A written in terms of one parameter, T. I have D written in terms of a different parameter, theta. So I got a problem in that I have to see how these relate to each other. I have to pick one parameter and stick with it. So I need to understand how T and theta relate to each other. And that's a simple matter of looking at that picture right there and realizing that, well, as T increases, theta decreases, and therefore the sum is always just it's constant. So it's in this case 3 pi over 2. Okay. Everybody with me now? Is that happy? Okay. So yeah, so we're in good shape now. So this theta that I've got sitting here, I can just plug in. Theta is 3 pi over 2 minus t. I'll use my angle addition formulas, and out comes d, also in terms of the t vector. So all together then, let's see here, all together, my a vector is that. My d vector is that, and a plus d gives me the p that I'm looking for, now parameterized. Pausing again for questions.
What is that angle addition stuff you mentioned?
Oh, yeah, right. Thank you for the reminder. Yeah, that's something I always need to point out every year. So there are formulas called the angle addition formulas for trig functions that were very standard at some point, let's not say how many years ago when I was in high school, but it used to be a total standard. And at some point, high schools just decided to stop teaching that, or at least many high schools did. I don't know why. It's not a good idea. The angle addition formulas are really important. So let me just write down very quickly what I'm talking about. So there's a formula for cosine of a plus b, and there's a formula for sine of a plus b. And it just happens very regularly that you need to know that, you have a cosine or a sine of a sum of angles, and you need to know how that breaks down in terms of sines and cosines of A and B. So I encourage everybody to look these up and memorize them. They just come up a lot, and they're really, really handy. So yeah, great question. Thanks for that reminder. Anybody else or any other questions?
I had a question about how you got T. Like, how did you decide that angle was T?
Oh, yeah. So, great question. Great question. So my idea was that when we first started this thing that I'm calling the D vector, right? That D vector was down there like that. And typically, I mean, I don't know. I tend to think of that when I'm first starting, that's where T is equal to 0. Right? As I roll, of course, this vector starts to kind of turn around that way. And so, the parameter that I would like to think of as time, that I would like to think of as starting at time equals 0, that parameter is just, it's this angle, right? It starts when that angle is 0. And then as time increases, T increases. Does that make sense?
Yeah, thank you.
Yeah, sure. Great question. Absolutely. Who else? Okay. All righty. So let's.
Sorry, I have another question. I didn't really understand how you got the formula for the A vector.
Oh, yeah. So it's a tricky move here, but the y coordinate is the easy coordinate. That's because the height is always a, right? That part's cool. Is that right? But yeah, so this first coordinate, though, how do I know this distance? And the argument that I make is that coordinate, the x coordinate, that's the x coordinate of this A point. That is the amount of road that has touched rubber, right? Again, you've got a bicycle wheel, it's rolling along the road. Some of the road has touched rubber, some is not. What we're looking for happens to be the amount of road that's touched rubber. And lack of slipping means that the amount of road that has touched rubber is the same as the amount of rubber that has touched road, which is that distance. And that distance is an easier problem because it's part of a circle, and arcs on a circle and all that.
Okay, thank you. Yeah, okay, that makes sense.
Good. Okie dokie. So, okay, last example of parametrizing. It turns out there's a really straightforward way to parameterize a line. All you need is a point on the line. And keep in mind, you can think of a point as being a of vector, what we call the position vector for the point. And then any vector parallel to the line. If you have that vector parallel to the line, right, then what you can do is just put together this little construction here, right, where you start with x naught, and then you add not v itself, but you add multiples of v. Right, and starting on the line and then moving by way of some vector parallel to the line will have you then remain on the line. So yeah, kind of a neat construction. This one conveniently lines all in some sense kind of look the same, right? So this same exact move will work for all lines, and is this one you just want to make sure you memorize. Because you're definitely going to need to parameterize lines. Okay. All righty. Okay. Now here's a sort of a stand back kind of perspective point about parameterizations, and a lot of people call parameterizations parametric equations. I kind of don't like that construct. I mean, they are equations, I know, but here's the thing: a parameterization is really kind of an alternative to an equation. You know, the way an equation works, right? What an equation is a point tester. You take some point that you want to know if it's on your curve, you plug it into the equation. If the equation works, then it's on your curve. If it doesn't work, then it's not on your curve, right? So literally an equation is a point tester. I think that's again, from a stand back point of view, good point of view about what an equation is. And a parameterization is not that, right? A parameterization is a different thing. And so, yeah, I know technically it uses there's an equal sign when we write a parameterization, but with the motivation in mind of trying to contrast it with this other way of describing a line, right, or a curve. I'd prefer not to call it parametric equations. I like to call it a parameterization. Okay, so anyway, importantly, what a parameterization is a point generator, right? A parameterization does not immediately give you a way to test if a point is or is not on the line. It just sits there and cranks out points. So you give me values of some parameter, plug in whatever value of t you like, and out comes every time, no matter what t you pick, you always get a point on the curve. So it's just, again, structurally a very different sort of strategy for how to describe a curve. And this distinction is, I think, a good thing to consciously, understand, consciously have in mind that these describe curves in these very different ways. And here's a really nice example of how you can take advantage of having this perspective. Question comes up. Here's a parametric curve, and I want to know what point or points, I don't know, right? But what possible points that are on that curve are also on the plane with that equation. Okay. So the big idea then is we're going to literally test the generated points, right? So keep in mind, this parameterization spits out points that are on that curve. I want to know, of those points on the curve, I want to know, are they also on the plane, right? Question. Are they also on the plane? How do I test if they're on the plane? Well, I toss them into my equation. You see, that's literally what I'm doing here. I'm taking over here, I'm taking the parameterized points, and I am literally putting them into that equation. Okay. So I'm putting them into that equation where you can see there's the X and there's the Y and there's the Z that I have plugged into this equation right here. Okay, so we generate points and then we test them. And what that gives us then is a sort of a foot in the door. If I'm going to generate a point that is going to pass the test, then, well, I need for this to work. And I do a little bit of algebra, collect some terms, and that tells you this, which then tells you, yeah, there's two values of t, and it's plus and minus 1. Okay, how we doing? Okay. All righty. Now, the following, I believe y'all have already seen. So I'm going to go through this. I'm going to say quickly, not super quickly, but I'm going to hit all the points. But anyway, I hope this should be review, namely symmetric equations for a line in R3. And so the idea is if you have a parametric line in R3, right, that's a line in R3, that's a point generator. What if I want a point tester? What if I want, I'm going to say an equation. I want something that plays the role of an equation. I want to be able to test whether a point is or is not on the line. Okay. I mean, bluntly, the way that I would decide is, well, there needs to be some value of t that makes the point that you want actually generated by that parametric curve. This is not a particularly useful right off the bat, but the way you decide with a parameterization is there needs to be a value of t that this parameterization generates that point. Okay. Okay, now that said, let me point out, this is actually 3 equations, and in those 3 equations, I can do some very innocent little algebra and rewrite those 3 equations as these 3 equations. I'm just in each of those 3 equations solving for t, right? So now let's look at what we have down here. Rather than there needs to exist a value of t that generates a certain point, now I have there needs to be a value of t that is simultaneously equal to all 3 of these things. And that's a lot easier to understand. If there is a single value of t that is equal to all 3 of those things, then all 3 of those things are equal to each other. And vice versa.
Next to the t.
I'm sorry?
What are those symbols next to the t?
Oh, yeah. I'm sorry. So this is standard mathematical shorthand. I assumed you would have seen those in 218, but I guess not. It doesn't matter. Anyway, this means there exists. Here, let me write it down. This is shorthand for there is or there exists. And this is standard mathematical shorthand for such that. So it's just shorthand. Yeah, good question. Thank you for the question. I'm sure other students didn't know that as well. Okay, so I think this is a nice little argument that these equations are equivalent to this trio of equations. And this trio of equations says that all 3 of these expressions here have to be equal. And so there you go. This is your point tester. If you want to know if your point XYZ is on your given line, well, you need for both of these equations to be true. If they are both true, you got yourself a point on the line. If either one of them fails, or certainly if both fail, but if either one of them fails, then I've got 3 things that need to all be equal to t, but they're different. How could there be a t that equals all 3 of them if they're different? Okay. By the way, if you want to turn this around backwards, it's really easy to do. Just don't forget where these equations come from. These come from the fact that all of these need to equal to t. So just remember that they're all t and then go backwards. So this then allows you to solve for x and vice versa, or likewise for y and z. Okay. All right, so that's section 1.2. We are now officially done 1.2. Moving along to 1.3, the dot product. Now, this is another one that I think y'all should have seen most about the dot product in Math 218. It's, of course, very standard construction in linear algebra. So here's the formula. I'm going to remind you again that, in these cases where there's stuff in the book that y'all have already seen or should have already seen in a linear algebra course, don't forget to actually go through that section of the book and identify and recall and make sure that you're polished on those things. So we are going to assume that you're good to go on all that stuff. So a bunch of stuff about dot products, make sure you're good. And then while we're here, I do want to point out that, something else you should have seen in a linear algebra class is inner products. And this, now that we're not going to really use inner products in this class beyond the dot product. But, it's worth mentioning that while we're talking about the many things you should know about the dot product, right, it is the model for the idea of inner products. It's inner product number one, right? Okay. All righty. Okay, now I have a little quibble with the book. As y'all have already heard me quibble about other things about the book. Look, this is just, it's terminology. So they can define the words however they want, but I'm unhappy with the fact that they use these two words interchangeably. They use these words to mean exactly the same thing, and you can see it right here. Perpendicular, aka orthogonal, as if they're exactly the same thing. That has not been how I've seen those two words used in the past, but more importantly, it's an opportunity missed. Because there are two different concepts that relate, that it'd be nice to have two separate words for, so we can discuss the differences between those similar ideas. So the point is, we have a geometric idea that relates to directions, and when two directions between those two directions define an angle, you got to have two directions to define an angle. And then there's this algebraic idea that sometimes dot products are equal to zero. So if we have two concepts and we have two words, I don't know, it seems to me this is a perfect match. Let's use one for one and the other for the other, right? So I think it makes sense to use perpendicular for the geometric idea. Note that means that the word perpendicular in my usage would be used only for non-zero vectors, because you need a non-zero vector to define a direction. The zero vector does not point in a direction, right? And then I would use the word orthogonal for this algebraic concept, namely the dot product being zero, which, again, for non-zero vectors means the same thing, but this more general thing, also works for the zero vector. Okay. All righty, so that's my little quibble. By the way, for whatever it's worth, sometimes this is the one we need to talk about, but sometimes this is the one we need to talk about. And so the difference is non-trivial. Okay. All right, quibble over. Moving along, y'all have seen this before, I feel sure, but certain things let's just go ahead and say it. If you want to find the unique unit vector pointing in the same direction as a given vector, nice, simple formula. Take that vector, divide it by its own magnitude. Easily shown that this is a unit vector. Proof's in the book, by the way, but it's very quick and easy proof. Think about how you would prove that, and it wouldn't be a bad idea to challenge yourself to write that down yourself. Okay. All right. Another thing you've probably seen before, but let's go ahead and do that anyway, is the idea of a component. And here's the concept. If you have a vector V, then you can say, okay, well, that defines a direction. And that direction having been defined, now, reasonable question. I've got a vector W here. To what extent does that W vector point in the direction? Forget about V now. To what extent does that W vector point in the direction that I have, this green direction? And so the extent to which it points in that direction is called the component. Okay, so easy to compute as it turns out. So a little bit of trig. Looking at this distance here is the magnitude of W. This distance here is, well, that's the component we're trying to find. And then I can say, okay, well, yeah, but then there's that angle, and trig gives us that simple relationship right there. That's what cosine is. Cosine of that yellow angle is blue over purple, right? Okay. So fine, then I can solve for what I'm actually interested in. I'm actually interested in that component. So we solve for it. And you could draw a line and say, okay, hey, yay, we're done. Here's a formula for the component. But clever observation is to say, you know, a magnitude times a cosine of an angle. Haven't I seen that before somewhere? That sounds, you know, there's an opportunity. Maybe I could connect this to a completely different concept that this reminds me of, right? And specifically, this little formula right here is super close to that, namely dot products, right? So when you notice that you've got something that looks very similar to something else, you know, making the connection can lead to something useful. So in this case, how do I make the connection? Well, I, you know, multiply and divide by magnitude of V. That turns the numerator into the dot product. And all of a sudden, then I have a handier formula for component. This, I say handier because I don't need to know the angle. And I don't have to do any trig. Right. So just knowing the vectors themselves, independent of that angle, no trig required, handy formula for computing that component. All right. Pause. Okay. Okay. Now, this is one way to write it. I have a preferred rewrite. This is a personal preference thing. You see that right there. We've got V over the magnitude of V. I remember that, right? V over the magnitude of V, that's the unit vector pointing in that V direction. That's the unit vector. Gosh, if you think about it, how would I define a direction if I were going to define a direction? You know, independent of magnitude, I just want to talk about just a direction. How would you define a direction? I mean, you know, arbitrarily, but kind of naturally, maybe the unit vector pointing in that direction. So this is that natural thing, the unit vector pointing in that direction. So I prefer to write this formula here as dot product with the unit vector, as opposed to dot product with the arbitrary vector that you happen to have had. But then, hey, by the way, side note, don't forget you have to divide by the magnitude of that arbitrary vector. It's just more, I think this is more natural. Okay. So it also leads to what I think is a really lovely, pithy, way to remember, way to understand components. Components are dot products with unit vectors. It rolls off the tongue really nicely. And this is the intuition that I have in my mind when I think about components, dot product with the corresponding unit vector. So I encourage you to think of it that way as well. Okay, pausing again. Okay. All right, now here's a related concept, projection. You'll notice we have kind of the same picture. We've got a vector that defines a direction, and then we've got another vector. And what I'm going to call the projection now, the projection is, it's not the distance. That's a component. It's the vector itself. Like if I were to look at the shadow vector, you might think of this as the shadow vector of W in this line defined by the vector V that we were given. Okay, so the projection, it's a vector whose magnitude, the magnitude is the component that we've previously talked about. Let me clean that up. So you got to make sure to distinguish between projections and components. By the way, I'm using the terminology as these terms are defined in the book. I've seen other books at some point in the past where they use these terms differently. So anyway, heads up. But in this class, projection is a vector, component is a distance, or as a magnitude. Okay. All righty. So yeah, so how do we compute this? My way of computing this is to kind of rely on what we talked about on the previous page and say, well, this vector that I'm looking for, that projection vector, I know the direction that it's pointing. The direction is the direction of the line. And how do I define the direction of a line? Well, with a unit vector pointing in that direction of that line. What's the magnitude? Well, the magnitude is, well, it's the component. And so there you go. So it's component times unit vector. And if you want to write that into algebra, then nice simple formula right there. So again, this is the way I like to think about it. Now there is an alternative. The formula that the book prefers, roughly speaking, the book takes this formula that we've got here, and then it says, well, yeah, but let's write that in terms of the original vector v and just kind of leave that all in there. And okay, you can do that. It's the same thing really, but I think it's easier to understand my way because you can most easily connect that to the direction and the component. Everybody with me? Let me do it like this. You can see more. There we go. Okay. All right.
I have a question.
Yeah, go ahead.
How is a component different from a projection?
Yeah, so the component is it's a number, it's a scalar. Projection is actually a vector. So right, so the projection is the vector. The component is just that scalar, that magnitude. Is that good?
Yeah, thank you.
Okay, sure. All righty. Okay, last comment before we go on to section 1.4 is that there are some nice examples in the book of how you can use vector algebra to prove certain facts about plane geometry. This is just kind of a recognition that that's there. It is ultimately all linear algebra. And you may not have seen that in your linear algebra class, but it's really linear algebra results. So I'm going to let y'all read those as a possibly even refresher, but it's also pretty straightforward reading, I think. Okay, so again, I have to make these tough choices about how to spend class time and how to, make how to give you the most effective use of this time, and I just don't think that's it. Okay, cross product. Another thing I think y'all have seen before. That said, I did write something like 8 pages of lecture notes about it because there's a certain point of view that I like to take on cross products that I think is much more satisfying. Ultimately, what I'm going to do here is a little different from what the book does. It's perfectly compatible, but I do the ideas in a different order, and the reasoning that I give is therefore it's very different reasoning between ultimately all the same ideas. Okay, so I like to start with clockwise, counterclockwise. The idea is if you have an ordered list of vectors. Now I emphasize that's an ordered list, right? Ordered in the sense that one of them is explicitly first and the other one is explicitly second. There is something naturally geometric about this. The order makes a geometric concept, and specifically, now notice, for example, if A were this vector, if that's the first one, and B were, let's say, that vector, that's the second one, what's geometrically natural about this being first and that being second is the way you go from first to second is unavoidably counterclockwise, right? Whereas now, instead, if A were, let's say, that vector, again, we have A listed first, and B were this vector listed second, well, now first to second is unavoidably clockwise, right? So the fact that this list is ordered, the ordering itself has a geometric interpretation. And so that's worth giving some names to. So counterclockwise and clockwise, I think, are the obvious way to describe these two cases. And most cases will be one of these two. There is, of course, the third possibility. It could be that these two vectors are parallel, or it could be that one of these vectors is the zero vector, or they could both be the zero vector, all of which, of course, mean the same thing, linearly dependent. Okay. All right. So when you have an ordered list, the geometric aspect of the list is described by one of these terms. Okay, real quick. These are mirror images of each other. I think that's a really easy pitch, right? And you can think of this a couple different ways. I mean, that when you do a mirror image through a line in a plane, then things kind of invert in a way. If you want, you can think of it as that the plane is kind of flipping over that line. It's kind of flipping through the third dimension, if you will, if you prefer. Anyway, there are mirror images of each other. Easy pitch. If you trade, which one is where, right? If you put the first one second and the second one first, that'll always change the order. Clockwise will come counterclockwise and vice versa. And again, pretty easy to see why that's the case geometrically. And lastly, I think this is worth observing. Rotating doesn't do anything, right? So if you have an ordered list and you then rotate both vectors by the same rotation, counterclockwise stays counterclockwise. Right, clockwise stays clockwise. I mean, so this independent of rotations thing is meaningful. Okay. All right. Okay. So why are we talking about clockwise, counterclockwise? I think it's a nice sort of warm-up concept for a more subtle, you might say geometrically unfamiliar concept, kind of like this in 3 dimensions. And it has to do, if you have an ordered list of now 3 vectors in space, right? So R3, not the plane, 3 vectors in space. So there are, in some sense, kind of 3 different versions. There's, there's the 2 primary, and then there's the sort of annoying, sometimes annoying coincidences happen, right? So let me go through those. I'm going to call them right-handed and left-handed and dependent. Again, I hope many of y'all, I hope, have seen this before, but I want to go ahead and say it for the record. The way you describe right-handed involves the human right hand. There's a certain gesture that you make with your right hand. You point your index finger parallel to your palm. You bend your middle finger the way that middle fingers want to bend. So, I mean, don't get cute, right? Right. So index finger parallel to the palm, and then middle fingers bending the way that they naturally do. And then, so with this arrangement of index finger and middle finger, do what you got to do to put your index finger along the direction of the first vector, your middle finger along the direction of the second vector. So I have the vector A listed first, so that one first. I have B listed second, so that one second. And you can see that in order to, according to the rules for my right hand, the way I would orient those as shown in that picture I'm looking at there is like this. And then you look now at your thumb and you notice which side, you look at the plane defined by those first 2 vectors, which side of that plane does your thumb point onto? And if the third vector, if it points on the same side as your right-handed thumb, then we call that a right-handed ordering. Okay. Now, let's play that same game, but with this list of vectors. A being first, but now pointing that way. B, the second one, now pointing over this way. And well, and then of course, C being third, I'm going to have that one still pointing up. But now let's play the game. Right hand, the way I'm supposed to have it, I need to point my index finger in the direction of that first vector, but now I need my middle finger to point in the direction of that second vector. And how am I going to do that? Again, no hand yoga allowed, right? But you're going to have to turn your hand over. Right? So now I've got my index finger pointing in the A direction, and I've got my middle finger pointing in the B direction. And now notice that my thumb points down. So does that third vector point on the same side as my thumb? No, it does not. So this is a left-handed, and by the way, as you can see, if I use my left hand, same rules, right? It works. So this is a left-handed list that I have here. So that list with these vectors is left-handed. Okay, so again, I hope y'all have seen this before, but if not, that's how that works. And of course, most random trios, most random, ordered lists of three will be left or right, but there are some, there's all these various different versions of linearly dependent where they don't neither the third vector doesn't point on either side of the plane, it points parallel to the plane, or one of the vectors is the zero vector. It's something annoying like that. All of those annoying cases are linearly dependent. Okay, a lot of the same properties. They're mirror images of each other. Easy pitch, right? I mean, your right hand is a mirror image of your left hand, right? If you were to trade not just the two vectors, if you were to trade any two of these vectors, trade the B and the A position, that changes the order, right? The action of switching any two vectors in the list, any two. Order is independent of rotations. Again, a pretty easy pitch. And I can turn my right hand around however I like, and it still remains my right hand, right? So it has the exact same geometric properties that clockwise versus counterclockwise had. This is a three-dimensional version of clockwise versus counterclockwise. There is, however, a fourth property that I think is worth pointing out, and that is if you cycle the list. So if everything kind of moves over one spot, or let's see, I guess I'm going the other way. If everything moves over one spot, and then the one that would have fallen off the edge goes back around to the other side, such as this, that preserves the order. And of course, there is no version of that really in for two-dimensional. Okay, so some theorems that you may, you know what, I know I'm out of time. That's where we'll draw the line then. Okay, let's see, let me stop share. So we got a bunch of stuff done today. Good to see y'all. Hope everybody has a great weekend. Don't forget, we are now done with section 1.2, and we are, let's see, where are we now? We are, we're also done with 1.3. So if y'all want to get started now, or this weekend on section 1.2 and 1.3 exercises, I think it'd be a good idea. And of course, not 1.4 yet. Okay, have a great weekend. See you later.
Thank you.
Thank you.
Sure.
Thank you.
Thank you.
Mhm.